We are going back now and picking up section 4.2. Hopefully you've already done the Desmos activity, so you have kind of an idea of what's about to happen. First, we'll start with Rolle's theorem, which is a special case of the mean value theorem. Rolle's theorem has three hypotheses that have to be fulfilled. It has to be continuous on the closed interval, differentiable on the open interval. Those are the same as the mean value theorem. The third is what makes it a special case. The endpoints have to have the same y values. So f of a has to be equal to f of b. So what that says in plain English is if you have a function that starts and ends at the same place, it has to change direction somewhere along the way. If it's increasing, it has to start decreasing at least once. And here's some pictures to show that. Let's make them bigger so you can actually see them. So there's four such functions. One is flat. Then all of the points on there satisfy Rolle's theorem because the tangent line is equal to the secant line at every point. This one, which is increasing then becomes decreasing, it has one place where the slope of the tangent line is equal to 0, which would be the slope of that secant line that connects the dots at the end, because they start and end at the same place. So, if it starts and ends at the same place, there's at least one spot in between where there's a horizontal tangent line. And I actually have this printed out so I can draw on it. So we have a graph of f. First off, does it satisfy the hypotheses of Rolle's theorem? Well, it's nice and smooth, so it's continuous. On the closed interval from 0 to 8. It's differentiable on the open interval because it's nice and smooth, doesn't have any corners. So continuous on the closed interval, differentiable on the open interval, and we're not calling it f. Yeah, we're calling it f. F of 0 is equal to 1, 2, 3, 4. F of 8 is equal to 1, 2, 3. 1, 2, 3. Yeah, 3, not 4. So they are equal to each other. So f of 0 equals f of 8. That means that it fulfills the hypotheses of Rolle's theorem. There has to be at least one spot where it switches from increasing to decreasing or decreasing to increasing. And here they are. Tangent line here, and then here's the secant line that connect the dots to the end. The function satisfies the three hypotheses of Rolle's theorem, first of all, and then find the number c that satisfy the conclusion of Rolle's theorem. So first off, we need to talk about continuous and differentiable. And we're going from -2 to 2. So it's a polynomial. Polynomials are continuous everywhere and differentiable everywhere. So it is definitely continuous on the closed interval from -2 to 2. And it is definitely differentiable on the open interval from -2 to 2. And I went ahead and put the function in for my f of x. And, oh, how about that? I have 2 there. We need -2 as well. So 2 is good. We want -2. And it's equal to -6 at both places. So f of 2 is equal to f of -2 equals -6. So that's all 3 hypotheses of Rolle's theorem. Now we want to find C that satisfies it. So I need to figure out the derivative. And I didn't write my function down, so I have to look over here. The derivative is 3x squared minus 4x minus 4. So the C will be whatever makes that thing equal to 0, because that would be the equation, the slope of the secant line that connects the endpoints. So I'm going to set 3c squared minus 4c minus 4 equal to 0 to see where it changes from increasing to decreasing or decreasing to increasing. And if you're on a test day and you don't feel like factoring, please go ahead and use your handy dandy calculator. But this one's not too bad. Only way to get 3c squared is 3c and c. And I want a 4 in the middle, and it needs to be negative. So if I have -2 times 3 is -6. Plus 2c gives me exactly what I want. So either 3c plus 2 is equal to 0. So c could be equal to -2/3. Or c minus 2 is equal to 0. So c could be equal to 2. So let's look back at Rolle's theorem. It says that there is a number in that open interval between A and B. So we want the C that is in the open interval between -2 and 2. So I choose you, Pikachu. I choose -2/3. Now, I went ahead and plugged this into Desmos. Here is the picture of f of x from -2 to 2. And there is -2/3. And that's where the tangent line is flat, as a horizontal tangent line. Let's move on to the mean value theorem. So, same 2 of the same hypotheses has to be continuous on the closed interval, differentiable on the open interval. Then there is a C that lives in that open interval between A and B, such that the derivative evaluated at C is equal to the slope of the secant line that connects the endpoints. It says equivalently, but I always just think of it this way. There exists C such that its slope is the same as the slope that connects the endpoints. Here's pictures, and hopefully you played with the Desmos and saw the pictures. This is the slope of the secant line. When I'm solving the problems, I do a couple of things. I calculate the slope of the secant line, I calculate the derivative, I set them equal to one another. That's the steps of the problem. And let's see, to illustrate, here is x cubed minus x from 0 to 2. So let's walk through it instead of just looking at the answer. Example 3. We have f of x, x cubed minus x, and we're going from 0 to 2. Polynomial, therefore, it is continuous and differentiable everywhere. So definitely from 0 to 2. So I'm going to figure out my slope first of the secant line. So m is equal to f of 2 minus f of 0 divided by 2 minus 0. I'm thinking maybe I can do this in my head because I have 2 cubed, which is 8 minus 2 is 6, minus 0 over 2 minus 0. So my slope is 3. F prime of x is 3x squared minus 1. So I set this equal to this. So step 1, find m. Step 2, differentiate. Step 3, set them equal. So 3x squared minus 1 is equal to 3. So 3x squared is equal to, add 1 to each side. So x squared is 4/3. So x is equal to plus or minus the square root of 4/3, which you could write as 2 over the square root of 3 if you want to. But we're only interested in numbers that live between 0 and 2. So that means we would let c be equal to 2 over the square root of 3. And there's the pretty picture. And here is the point. C is the square root of 4/3, 2 over the square root of 3. Let's practice some more. So f of x is just the square root of x. And we're looking at the interval from 0 to 4. First off, we acknowledge that this is continuous. From 0 to 4. Not differentiable at 0, but that's okay. Things are never differentiable at endpoints anyway. So on the open interval from 0 to 4. So step number 1 was to find the slope of my secant line. F of 4 minus f of 0 over 4 minus 0, which would be the square root of 4 minus the square root of 0 over 4 minus 0. Two over 4 is a half. Step 2, find my derivative. 1/2 falls down. Subtract 1 from the exponent. Step 3, set them equal to each other. So 1 over 2 times the square root of x is equal to 1/2. Cross multiply, 2 is equal to 2 times the square root of x. So x is equal to the square root of 1. And there is the graph of the square root of x from 0 to 4. And we are convinced that our c is equal to 1 because 1 lives between 0 and 4. If we wanted to write down the equation of the tangent line, it would be y minus my y coordinate, so y is equal to the square root of 1, so the 0.11. Y minus my y coordinate is equal to slope times x minus my x coordinate, which is exactly what I have right here, except I was too lazy to plug in f of 1. And then this is the equation of that secant line. And you can see that they are parallel to one another forever. Get rid of those. Go back and do some more practice. I think I'll let you do the next one on your own, y equals x squared over 9 from 1 to 4. And then we will meet back here and compare answers. I just acknowledge that rational functions are continuous and differentiable over their entire domains, and the domain of this rational function is everything except 0, so we're good to go as far as the hypotheses. I calculated the slope, which I plugged in the calculator. I didn't do all that arithmetic. I got 13 over 12. I took the derivative, and I divided it into two pieces. You could have low, high, quotient rule tried. You would have ended up with the same thing. It would have looked a little different. You would have had just one thing sitting on the right-hand side of this equation. I just thought that was going to be easier for me. So I set 13 over 12 equal to 1/3 over 3 plus x squared. I subtracted 1/3 from each side, and 1/3 is 4 over 12. So 13 over 12 minus 4 over 12 gave me 9 over 12. I cross multiplied. I got two options, plus or minus 2. So my c that I chose was the one that lived in the range I was interested in, 1 to 4. I plugged 2 in just to see what the y coordinate was so I could write down the equation of the tangent line, even though over here I didn't bother. I just let Desmos do the work for me. If you want to do the secant line, you can do the same thing. It's y minus your y coordinate is equal to slope x minus your x coordinate for one of the endpoints. And I had plugged those in my calculator, so I already had that one figured out as well. Okay. Hopefully you made it through that one. We'll do this next one together. Then we'll look at a real-life application. You can, spoiler alert, see what's coming up. So this time y is equal to the negative, and I'm going to write it as a square root just because, minus 2x plus 6. And we're looking at it from negative 2 to 3. So radical functions are continuous and differentiable on their domains. What is the domain of this thing? Well, negative 2x plus 6 has to be greater than or equal to 0. So negative 2x has to be greater than or equal to negative 6. That's what I get for doing arithmetic in my head. And so x has to be less than or equal to 3, because when I divide both sides by 2, the inequality flips direction, just like you learned back in pre-calculus. Oh yeah, that's another reason we learned to solve inequalities. Alrighty, so since it is continuous from negative infinity to negative 3, it's certainly continuous from negative 2 to 3. And it's differentiable everywhere except at that end point, but that's okay. We don't need it to be differentiable at the end point. It needs to be differentiable on the open interval from 2 to 3. So, hypotheses, check. Slope of the secant line would be the negative of the square root of negative 6 plus 6. So I plugged 3 in, minus negative the square root of, let's plug negative 2 in, that gives me 4 plus 6. All of that divided by 3 minus negative 2. Well, that's 0. That's friendly. Minus minus is plus. So I have square root of 10 sitting on top and 5 sitting down below. Derivative y prime is equal to, I have a negative sign hanging out, so minus 1/2 falls down. You might like looking at it over here. 1/2 falls down, minus 2x plus 6 gets raised to the minus 1/2 power, and we multiply by the derivative of the inside. So you go away with you. I'm left with x over the square root of minus 2x plus 6. Step 3, to set them equal to one another. Fun stuff, cross multiply. So 5x is equal to, x shouldn't be there, that derivative is just plain old 2. That whole thing canceled away. That should be a 1. I know. I wasn't listening. You were trying to tell me that the derivative of negative 2x is just negative 2. So I don't have an x here at all. I just have 5 is equal to, and I can put all of this under one radical, 10 times minus 2x plus 6. Again, thinking back to pre-calculus, we learned to solve radical equations for a reason. So we could do it now. So we square both sides, this radical just goes away, and I think this is a really good time to distribute that 10 through the parentheses. So now I'm going to subtract 60 from each side. So negative 35 is equal to negative 20x. So 35 over 20 is equal to x. 5 goes into 35 7 times. 5 goes into 24 times. So I get 7/4, and that does live between negative 2 and 3. So this is my C. So we're supposed to graph the function, the secant line through the endpoints and the tangent line. And handily enough, I did that already. Get rid of the old one. Here's my function from negative 2 to 3. There is my secant line, and here is my tangent line. And you can see that it goes through the point. There it is. 1.75, which is 7 over 4, and negative 1.581. I didn't plug it in. It was not a pretty number, not a nice friendly whole number. Okay, a couple of good examples of the mean value theorem. Let's look at this real life application. So, you are driving on the New Jersey Turnpike. Toll booths A and B are 30 miles apart. The speed limit is 65 miles per hour. You pay the toll at booth A at 1:32 and at toll booth B at 1:56 p.m. You receive a speeding ticket in the mail. Can you use calculus to contest it? Or can they use calculus to prove that you deserve it? So let's see. So what does that mean? Figure out our average rate of change over that time period. So we're thinking of miles per hour. So that's miles over hours. We went 30 miles. Now it was 1:32 when we were at toll booth A, and it was 1:56 when we were at toll booth B. So if we take 56 minus 32, that's going to give us miles per minute. Darn. So what I need to do is change that to hours. 56 over 60 minus 32 over 60. I'll take a minute and plug that in my calculator. Meet you back. So I multiplied numerator and denominator by 60 to get rid of that fraction over a fraction, and then all I had to do was take 30 times 60 and divide it by 56 minus 32, and I got 75 miles per hour. That was your average speed. But is there any proof that you were ever going over 65? Well, yes, because at some point between toll booth A and toll booth B, you are going exactly 75 miles per hour. Now, the fact that it's greater than 65 means you were probably going even more than 75 at some point too. But no, you cannot use calculus to contest that ticket. There are some consequences of the mean value theorem. If the derivative is equal to 0, then f is a constant. And if two different functions have the same derivative, they can only differ by a constant. But remember, that's only true if it fulfills the hypotheses of the mean value theorem. Alrighty. So, quick summary, make sure it fulfills the hypotheses, because I know you have a test next week. And what are those hypotheses? Continuous on the closed interval, differentiable on the open interval, calculate your slope of your secant line, f of b minus f of a over b minus a, calculate your derivative, and then find c, because f of c is that very special number where the derivative is equal to the slope. You can do it.